Up to this point, we've mainly been discussing derivatives. In this chapter, we are going to turn our attention to integration. Just like the book does, let's review a little before we get into our new version of integration and look at how we defined integrals, specifically definite integrals, back in Calc 1. So let's say we have a function, f of x, of one variable x over a closed interval, ab. We we defined our definite integral, the integral from a to b of f of x dx using rectangles. Let's actually look at a specific example and kind of draw it out. So I'm going to look at the function f of x is 1/5 x cubed minus 18/5 x squared plus 20x minus 31, where I've chosen numbers here to make things actually look nice when we draw it out. So here I go ahead and put in my function. And we're going to use the interval from 3 to 9. So let's go ahead and even just put those in there. X equals 3 to x equals 9. That's what we are concerned with, and we'll kind of zoom in a little bit on it. Now, there's a couple things we can do here. First of all, one thing you may not have noticed is that GeoGebra does have an integral function, or integral feature, you could say. I tell it that I want to integrate the function f that we've already defined up here, or you could put a actual formula in there if you want to. I'm going to go from 3 to 9, and it'll go ahead and not only display the actual integral, I don't even need the function in there to see that, but it also gives me the actual value, or at least the approximate value of that integral. We'll just put that down there. Actually, maybe we'll even rename it. You call it int for integral. Now, if we want to look at rectangles, we could try to define a whole bunch of rectangles in here and do this all by hand. Again, I'm going to try to make use of some of the features of GeoGebra. Um, let's first put in a couple sliders. I'm going to go ahead and use these. So I'm going to have a slider A, which is going to give me values between 0 and 1. You'll see what I'm going to use that for in a moment. But I'm also going to put in a slider that's just going to be integer values, and it picks in for that. And I guess let's go ahead and just keep the 1 to 30 that they have here. So GeoGebra has another nifty feature called rectangle sum, and I'm just going to go ahead and use their suggestion here and fill them in. So this actually will give me rectangles corresponding to some function over an interval. So I'm going to give it the function f. My starting x value, of course, we're going from 3 to 9, so we go 3 to 9. The number of rectangles, that's why I have this slider in. So I can actually change how many rectangles I'm looking at. And position for rectangle start, that's a little bit confusing, but it kind of is a, for each of our rectangles, we have to pick a point in the interval that we're working with. And then we use the value of the function at that point to determine the height of our rectangle. What this is going to do is it's going to kind of pick the sample point on a proportion of the little subinterval that we're working with. It goes from 0 being the leftmost endpoint to 1 being the rightmost endpoint. And you could even use the midpoint rule and use 1/2 in there as well. Again, that's why I picked the slider A. That'll give me numbers between 0 and 1, and that'll allow me to actually change that if I want to. But this, when I go and put that in, because I only have n equals 1 here, so we're only using one rectangle course, that's going to go over the entire interval. And I'm using, because a equals 0, I'm using this endpoint over here as my value of the function. If I change this, I'm going over values. So I'm picking this point here as we go around, and you can kind of tell as we get up to here, it reaches its maximum. As we go a little bit past that, now we're picking points along here until we go all the way around. But you can kind of tell that while our integral actually has a value of 15.6, that's the area under the curve, using one rectangle we can get values as high as 26 and as low as 5, around there. But if we pick more rectangles, we kind of limit ourselves to a smaller range of values that we can get out from looking at the sum of the areas of these rectangles. And it's better and better the more rectangles we use. And as we go off to infinity, as we allow the number of rectangles to go off to infinity, we get closer and closer to that true integral value. That's how we defined our definite integral back in Calc 1. We called the sum of such rectangles a Riemann sum. So if we were to write this out, we would write this using our summation notation. We'd have rectangles numbered from 1 to n, where n is the number of rectangles we're using. We'd use a height of the function at some sample point. We'll just call it xi star is going to be some sample point in the ith subinterval, and we put that value into our function and get out a height. And then we use delta x as the width of that rectangle. For what we were doing just a moment ago, delta x would be our 6, which is the from 3 to 9, that b minus a basically, divided by the number of rectangles. Though in general we don't have to use equal width rectangles. In general, we might write something like delta xi as the width of the ith rectangle. And as the number of rectangles goes off to infinity, this will turn into our integral of this function. And if you really want to, you can find out what that is by hand. GeoGebra did tell us it's about 15.6. That's probably not exact, but maybe it is. I don't know. The 0.6 I actually work with all the fifths that I have in my formula. But just be aware that that rectangle sum, the one that we just used right here, isn't really giving us every way to make a Riemann sum. For one thing, like I just mentioned, the rectangles don't have to have the same width, and we can actually pick sample points that aren't necessarily the same proportion every time. We might pick the left-hand endpoint to make our rectangle over here, but over here we pick the right-hand endpoint, or maybe here we pick the midpoint. It really doesn't matter. It's as long as we are making sure our rectangles in the limit are having 0 width, and we pick some sample point in that interval, we actually will get the correct limit, assuming it has a limit. If it doesn't have a limit, then we can't integrate it. But the fundamental theorem of calculus does say that as long as you have a continuous function, that limit will exist. But if you really want to get into all that complication of that, you'll probably have to take a course in advanced calculus. But that is Math 547, and mostly just math majors take that. So don't worry too much about that. But I wanted to jog your memory of how we define the definite integral and how it works with calculating areas underneath curves. Because that's the idea that we really want to capture, but in a three-dimensional context. So what we're trying to do here is we want to take a function of two variables, so something f of x, y, And we want to look at it over some closed region in the plane. So we'll go ahead and maybe call that D. So this is going to be a closed region in the plane. Let's actually even say closed and bounded. Kind of the same kind of regions that we were looking at when we were looking at maximizing functions, finding absolute maximums and minimums. And we want to see what is the integral of this function over that region. And we'll kind of get into what that will even mean in a moment. But before we even get into this very general idea, we actually want to start with an easier region. So instead of this more general D, we're going to instead work with some R, which is a rectangle. And we'll say our rectangle will look something like AB crossed with CD. And what I mean by that is if I draw our axes out here, we'll look at values of x between A and B and values of y between C and D, and this will define a rectangle. So in other words, you can say it's all the points x and y where x is between A and B and y is between C and D. This notation here with the product notation is just a mathematical shorthand for this concept. But the book brings it up, so I definitely want to do that too. Plus, I kind of rather write it this way than write it that way. But the idea here is that the first factor here gives limits on x, the second factor gives limits on y. But we're basically taking this rectangle here instead of some more blobby D that we'll look at a little bit later. So that'll be the next section. But we want to see what does it even mean to integrate this function f over this rectangle. Well, maybe let's look at a particular example. Let's say f of x, y, is going to be the function. I'm going to go ahead and include some fractions like I did in the previous example just to keep things nice and small. So I'm going to take x squared plus y squared because that's a fairly nice function that's not too easy to work with. And I'm just going to divide it by 20 just to keep the number smaller. And I'm going to look at my rectangle as 1, 2 cross with 2, 3. And we'll go ahead and plot that. So I've already got a couple sliders prepared, but we're going to use those a little bit later. But our function f of x, y is going to be, like I said, x squared plus y squared. And then we divide by 20. So we get this thing here. It's a paraboloid. I'm concerned specifically with the region between 1 and 2 cross with 2, 3. So let's go ahead and put that in here. So what I've done here is I defined our corner points, 2, 1, 1, 1, 2, 1, 3, 2, 2, and 2, 3, and then I used their polygon feature to go ahead and make that quadrilateral or that rectangle. I think I messed that up a little bit. Yeah, you have to be careful to go around the polygon or the rectangle, not go along the diagonal. You'll confuse it. But basically, I've got this square down in the xy plane, and I'm looking at the function specifically over that square. And let's kind of cut out what we don't need from this function. So here I've taken only the piece of our function that's over that square. I used a function called surface. Don't worry about exactly how this is set up. We'll get to how we can define stuff like that a little bit later. But the idea here is I'm only looking at the portion of the surface that's above our square. Kind of losing our axes there, but oh well. And what we can kind of do is treat this as kind of a solid. So here I've gone ahead and attached the corners of our square to the corners of this cutout of our surface. And we've kind of got this solid piece here. If we imagine all the points between the actual square and our surface. And what we're really trying to do here is find the volume of this solid. So just kind of the exact same way we'd find the area below a curve, we're finding the volume below a surface, or above the xy plane specifically. And that is going to be our main driving idea behind all of this. But how do we actually do that? Well, we're going to do the kind of the same thing that we did in Calc 1, where we used rectangles and actually break up our defining rectangle down in the plane into a bunch of sub-rectangles and look at the volume of boxes over all those sub-rectangles. So here I've taken a little sub-box down in, or sub-rectangle down in our main rectangle down here. I've used the sliders A and B to define this point here, and then I use a little offset to make the rest of it. I picked a height. Specifically, I picked the point right in the center of the box and used the value of the function at that point to define the top of this box. And we're looking at some box in here. This will have a volume that is actually fairly easy to calculate as long as we know the area of this base and the height of the box. And we could move this around, see exactly how it changes, and we'll kind of think of having a whole bunch of these boxes and adding up the volume of those boxes. Specifically, the volume of such a box, so maybe we'll do this on another page. So the volume of a box is going to be the value of the function at whatever sample point we're using. I'm just going to put f star y star. This is in the example that I put here. Like I said, I picked the point right in the middle, but theoretically we could pick whatever point we want to. And then we would multiply that by delta A. This is just representing the area of the subrectangle that forms the base. And so in this particular case, it's the area of this little square inside the bigger square. We don't have to use squares, but that's just what I have in here. Now we do need to make a whole grid of these little subrectangles. And GeoGebra doesn't really do that for me very easily, so I'm going to leave that more to your imagination exactly what that look like. The book does have a few pictures that might help with that. But let's go ahead and actually kind of draw that out, or draw at least the sub-rectangles, maybe without the actual surface itself. So we're going to start with our, let's say here are x values going from A to B. Here's our y values going from C to D. And we would break up our x interval into a bunch of smaller regions. Maybe this would be A1 basically is our x0, then we have an x1, x2, all the way until we get to some x in minus 1, and then b would be x in. So we have in different subregions or down here on the x values. For our y's, we do kind of the same thing. We'll break this up into a bunch of pieces. C would be our y0. Then we have y1, y2, all the way to some y in m minus 1. So we don't necessarily have to have the exact same divisions as for x's as for y's. So we use n and m. And then d would be ym. And then we just have this grid. And I'm not doing a good job making super straight lines here, but hopefully you get the idea. Yeah, that is not turning out very nicely. Oh well. But the point here is that we have a bunch of sub-rectangles, and imagine that they actually rectangles, not like I've drawn them. And each of those rectangles will be called something like Rij. So you could say this is the actually let's put this one. This would be rectangle. It'd be the third along the base, so 1, 2, 3, which starts with x2, and then it'd be the third along the y-axis as well. So it'd be R3, 3 would be that rectangle there. This would be R3, 2 because third along here, 2 along there, and so on and so forth. So we have all these Rij's. Technically, we could write these as a product like we did before. So this would be xi minus 1 to xi. It's is our range on our x values. So here, let's say R32 actually starts with x2 and goes to x3. And then the y values do the same kind of thing. We have yj minus 1 to yj. Inside each of these boxes, we have to take some sample point. So let's say in R32, we're to pick this point right here. In R33, maybe we pick the point over here. It doesn't really matter as long as we pick a point for each of our boxes. And so the sample point for Rij, we're just going to label that as Xij star, Yij star. That's going to be our sample point. And we technically picked one for each of our rectangles. And then the volume of that of the box over that, maybe we'll just call that Vij. It's the volume of the box over Rij using the sample point and plugging that sample point into our function of two variables. Remember, we're just following this formula that we have here. So this is f of xij star, yij star, and then we use the area of that rectangle. So the area of Rij is, let's say, Aij. If you follow the way the book does it, it goes ahead and assumes that we do equally spaced divisions along each of the axes, and so each of these will actually turn into the same size, and so have all the same areas of their subrectangles. That's not actually required, though it's usually a little easier to do the computations that way. If you're going to do them by hand, that is. We'll be looking at better ways of approaching it than what we're doing right here. But I do want to give you the idea behind everything to begin with. So this is the volume of one box. And then we have to add up over all of the possible boxes. But keep in mind, we do have two indices here. We have an I and a j. We have to sum up over I and j. That means our Riemann sum that we're going to get, should be IE, Riemann sum, is going to be a sum over the i's, so I is going from 1 to n, and a sum over the j's, so j is going from 1 to m. And then we just put this formula. We have the f xij star y ij star delta a ij. We could say it's a double sum because we do have to sum over each of those. Because if we just summed over the j's and kept maybe I fixed at 1, we'd only be looking at these rectangles in this column here and not all of them. If we have a fixed I, we're only looking at one column at a time. If we use a fixed j, we're only looking at one row at a time. We have to go over all possibilities. So we have to do this double sum. Of course, that's not where we're going to stop with this. We're going to let the number of rectangles go off to infinity, which means that we let both m and n go off to infinity at the same time, and we also make sure that the area of our rectangles goes to 0. We don't have to worry too much about that if we're picking equal size rectangles, but if we do the more general version, then we do have to add in that extra criterion that the area of the rectangles will be going to 0. As we do that, we get better and better approximations for the volume underneath the surface, and the limit is something that we'll call the double integral of the function f. So we take our limit as m and n go to infinity, and we get this, what we'll use the notation of two integral signs with the rectangle labeled down below of our function, and we'll use dA because we were using delta A before. Now, the book tries to make this somewhat formal, and again, if you're truly interested in all this kind of stuff and making all this stuff really precise and everything, you'd have to take a course in advanced calculus. But the main thing is that we have a way of essentially saying what the volume should be. In fact, as long as we are assuming that our function is positive, that doesn't dip below the xy plane, then we'll say that the volume of the solid that lies above that rectangle and below the surface is given by this double integral. If the function is not always positive, we're not really representing a volume per se, but we're going to basically do what we did in Calc 1, where instead if we had a function that didn't stay positive, what we do is take the part that's above the x-axis and subtract the stuff that's below the x-axis, and that's going to be the value of the integral over this whole region. So for volumes, we take the volume that's above the xy plane minus the volume that's below the xy plane, and that will be the double integral over that entire rectangle. So it's really basically we're allowed to deal with negative volumes as long as they're below the xy plane. So hopefully I don't have to explain that too much more. Let me know if that's confusing at all. But the point is that we can always kind of fix it if we don't want to have the stuff underneath. So if in this particular case, we're going from a to b of some function f. If we actually wanted to find the volume inside there, what we could have done instead of just integrating over f of x, which would subtract the two areas, we would integrate over the absolute value, which would be essentially taking the stuff that ends up below and flipping it up to the top, so we end up adding the areas together instead of subtracting them. We can do exactly the same thing with the volume if we want to. Just use absolute value. It gets a little bit complicated maybe to calculate the actual integral that way. That basically ends up meaning that we have to split it up into multiple integrals. But we will get into some more of that kind of stuff in the coming sections. So that's a little bit beyond what we want to do right now, because splitting this up can be a little bit complicated when the where we're going to split up will not necessarily be a straight line. Won't result in rectangles that we're integrating over. Now, I could subject you to computing some of these double integrals by hand, and the book even goes through a version of the midpoint rule for doing exactly that. But I'm going to go ahead and just skip to the way that we'd like to compute double integrals by using antiderivatives. I'm going to save that for the next video. So meet me in that one, and we'll actually figure out how to compute these things without having to take a big sum, a big double sum over values of the function, and then try to talk about limits, which gets really messy. Once we can use antiderivatives, this will be a lot smoother. So I'll see you in that video.